In section 7.2, we're going to take a look at a topic we really haven't seen so far in calculus, and that's the topic of volume. The way we're going to determine volume is using something called the disk method. And if you kind of want to see this picture right here on this opening slide, if you wanted to find the volume of this kind of vase-looking shape, we don't have a formula for that, unlike cylinders and cones and stuff like that. So theoretically, like we did back when we were trying to find area, is we could use a simpler shape to approximate the volume in this case. And you'll notice we have these, I guess, what are called disks, and that's why this is called the disk method. We can use these disks to approximate the area of this vase-looking shape. Of course, it wouldn't be the exact area, but it wouldn't be that difficult to find the volume of each of these disks, or cylinders if you kind of want to view them that way, and then add those up. Fortunately, though, we don't have to worry about approximating these volumes because we have something in our toolbox that lets us add up an infinite amount of things. And that tool was called integration. When we're trying to find area, we integrated, which meant we were adding up an infinite number of rectangles. In this lesson, we're going to try to find volume with these disks. We're not going to add up 10, 20, 30, or however many. We're going to add up an infinite amount of those disks so that we can find the exact volume of these shapes that we're going to be looking at. Okay, so how do we form, or how do we generate these three-dimensional shapes that we're going to try to find the volume of? Well, the first thing you have to kind of realize here is that this topic, or these kinds of solids, are called solids of revolution. The reason they're called solids of revolution is because we're going to take a shape, for instance this rectangle you see here, and revolve it around a certain line or an axis. In this particular case here, I'm going to take this rectangle and rotate it about this line. Now you kind of have to do an okay job of kind of visualizing this in your head. If you imagine taking this rectangle and flipping it about this line right here into 3D space, so it would be kind of coming out of your paper, back into your paper, and out of your paper again, what we're going to form is this shape. And I'm not sure if you would have been able to see that visually in your head without seeing this picture, but that's the idea. If we take this rectangle and rotate it about this line of axis, or this axis of revolution, we're going to form what is called a disk. I guess realistically we don't have to call this a disk. A disk is really just a cylinder. I guess the reason we call it a disk is we've taken our typical cylinders and flipped it on its side, and it's a lot thinner than the tall cylinders I guess you're used to seeing. But either way, these are just cylinders, or ultimately disks. So what if we wanted to find the volume of this single disk? Well, that would just be a matter of taking the area of the disk, or the area of the base, if you want to remember how to find volume of three-dimensional shapes. The volume of a three-dimensional shape would just be the base times the height, but it's the area of the base times the height. So of course it's the area of the disk, or the base, times the width of the disk. Of course the radius of the disk, I'm going to call this big capital R here, and then the width of the disk I'm going to call small w. And there's actually a reason why I'm using capital R. I know we're used to using lowercase r, but make sure you're noting that I'm on purpose using that capital R. A little bit later we're going to need to use a lowercase r for something else. So how do we find the volume of this one disk? Well, it's just the area of the base, which is a circle, so pi r squared, times the width of the disk, or the height of the disk, if you want to call it the height that's been flipped on its side. So we really call it width. So again, the volume of this disk would be the area of the base, which would be pi r squared for the circle, and then the height of the disk, which again is really going to be called the width of the disk because it was flipped on its side. Okay, now that we know how to find the area of a disk, remember, we want to find a volume using disks, and we want to add up an infinite amount of those disks. So now that we have the volume of a disk, let's see what these exact volumes of these shapes are going to look at. So here we have this weird shape here, shaded in blue. just defined by some function. I guess this could be just the function f of x if you wanted to call that your function f of x. And what we're going to do is we're going to take this shape in blue and rotate it about that line, that axis of revolution. If you imagine rotating that about the x-axis, this would be our x-axis. I'm not sure if you can visualize what that would look like, but ultimately, of course, we would just take this shape above the line and kind of flip it down below the line, kind of up and down, in and out of your paper, if you can visualize what that would look like. And then we would get this shape, kind of a cut off Hershey kiss, so to speak. And you'll notice I could stick in a bunch of these discs into this shape, and I could find the volume of each of those discs pretty easily, now that we have that formula that you saw in the last slide. But of course, that would just be an approximation. We want to find the exact volume of this shape, whatever you'd want to call this shape. So ultimately, we need to realize is the volume of these solids is the sum of the volumes of the discs. But I guess there's maybe a word missing here that you might want to take note of. It's not the volume of 10 discs or 20 discs, it's the volume of an infinite amount of discs. Again, how do we add up an infinite amount of things, or in this case discs? Well, we need to integrate. So let's go ahead and take a look at the two ways we can have these solids of revolution. We can either rotate around a horizontal line or a vertical line. So let's take a look at the first case. If you take a shape, some area, which you guys see here in blue, and you rotate it about a horizontal line, and it doesn't have to be the x-axis, we need to realize that we need to put in our representative rectangle. If you recall, this rectangle right here is called our representative rectangle. And all that's doing is representing that rectangle that's ultimately forming a disk when we rotate this shape about this horizontal line. So anytime you have a horizontal rotation, again, it doesn't have to be the x-axis, we're going to draw our representative rectangle in vertically. So ultimately, it gives us this formula that we're going to have to know to do these types of problems. The volume of this solid when you rotate it about a horizontal line is going to be pi r squared dx from a to b. And again, this integral symbol from a to b is telling us we're adding up an infinite amount of these elements. And again, the elements, of course, we're using here are disks. So this shouldn't be a surprise that this is the formula. The reason this is the formula is we just need to add up the volume of these disks. The volume of a disk is pi r squared times our width. And again, the width here is a little change of x here that we're going to write as a dx. So really, there's a lot of formulas that we need to know in calculus, but hopefully you're not viewing this as some extra formula. As long as you realize the formula of a disk is just pi r squared times w, then this shouldn't really be a big deal to kind of commit to memory. Okay, so what if we rotate about a vertical line? Could be the y-axis or just some other vertical line. Well, really all that changes is just the orientation of things. If you rotate about a vertical line, you're going to need to draw in your representative rectangles in horizontally. And ultimately, if you remember from 7.1, if you ever need to draw a representative rectangle in horizontally, that really just means you're doing everything in terms of y. So same exact formula, pi r squared times our little change, but now it's a change in terms of y, which means the radius needs to be in terms of y. So hopefully this will kind of just serve as a nice overview for looking back at attempting these problems, but ultimately looking at some examples of how this works is where we're going to go from here on out. Okay, so Before we even start this problem, one of the things to point out, especially if it's not given to you in a problem, is you really need a good looking graph sketched to really make these problems work out good. I think that's really the main key for these problems, assuming you understand the process of setting these up, and certainly the integration after that, which we've practiced, shouldn't be too big of a deal, I hope. I think really the key for these problems is getting a nice looking graph so you can set up everything and make sure the setup of your integral is correct. So here we want to find the volume of a solid formed by revolving the region bounded by the graph of f of x equals the square root of x, which you can see right here. And we're going to rotate this shape from 0 to pi about the x-axis. So what does that really kind of leave us with? Well, you don't always have to draw this in. It's kind of up to you if you want to draw this in, but really in your head you have to imagine taking this shape that's above the x-axis right here, which is what we're looking at, and we want to rotate that about the x-axis, which will give you a shape roughly like that. You never really want to draw on that bottom part. It might serve to kind of confuse you a little bit, but visually in your head I hope you're visualizing that kind of a shape in 3D space. Here I've kind of drawn that for you in this animation, but that's the idea. If we take that function, square root of sine x, from 0 to pi and rotate it about the x-axis, we'll get this kind of football egg looking shape. But ultimately, that doesn't matter so much as just looking at this picture. So if you refer back to that last slide, if we rotate about a horizontal line, in this case it's the x-axis, we need to draw a representative rectangle in vertically. And the main key in doing this is you need to realize that the height of that representative rectangle is the radius of a disk in the three-dimensional shape. So we can go ahead and start with our formula. We know we're rotating around a horizontal line, so everything's going to be in terms of x. So really it comes down to, what is r of x? What is big R of x? Well, if you notice, the height of this representative rectangle, which is the radius of a disk, corresponds to this idea we learned in 7.1 of finding the height of these rectangles. And hopefully you remember that to find the height of these rectangles, it was just taking the top minus the bottom, whatever the top of the rectangle is touching, and subtracting away whatever the bottom of the rectangle is touching. So if you notice, and I've drawn in a couple disks in this extra visual below, the height or the radius of this disk is the function square root of sine x. I guess if you want to be more thorough with this, we would really be taking what the top of the rectangle is touching, which is the square root of sine x, and subtract away what the bottom of the rectangle is touching, which would of course just be the function 0 because it's our x-axis. So I hope when you're looking at this, you're kind of seeing what we did back in 7.1 when we were trying to find area in terms of setting up these representative rectangles. If you want to find the height of a representative rectangle in a vertical orientation, we just take the top of whatever it's touching minus the bottom of whatever it's touching, and that's the height of that rectangle, which again corresponds to the radius of these disks. Okay, hopefully that all big long discussion makes sense now, because after that we're just going to use our integration skills to solve these problems. I think when it comes down to doing these problems, the setup is going to be the big challenge. After that, maybe there'll be a few hard integrals from time to time, but I think you'll find a lot of these to be pretty straightforward and easy. So if you focus on the setup and really trying to understand that portion of these problems, you'll be even more successful doing these. Okay, so of course we don't really need that minus 0, and if we square a square root, it just goes away. And now we're left with a nice simple integral. We have sine x, which becomes negative cosine x, and when we apply the fundamental theorem of calculus, when we plug in pi, we'll get cosine of pi, which is negative 1. We have another negative, so that's positive 1. When we plug in 0, cosine of 0 is 1. But since it's negative 1. So really, I didn't really draw this or animate this in, but this was really 1 minus negative 1, which of course became a plus 1. One of the very common famous mistakes people will make is to forget about this pi. If you're going to make any mistake with these problems, I could imagine for a lot of you, you might forget about that pi in the front. As long as you don't, we're good to go here. 1 plus 1 is 2, so the volume of that egg football kind of shaped 3D figure you saw from before, the volume of that shape is 2 pi. Okay, here we have another example, slightly different than the one before, but ultimately it's using this idea of rotating an area about a line and making one of these things called a solid of revolution. So again, I think the main key to doing these problems is to get a good looking graph. Unlike the last problem, which gave you the bounds of what you were looking at from 0 to pi, was that last problem, here they do not tell us from where to where our area is. If you remember from 7.1, when you're given these problems, they're really called bounded problems. We have to find the bounds of the area we're looking at. So to do that, we need to find where these two functions intersect. So to do that, we just need to set them equal to each other. F of x is 2 minus x squared, g of x is just equal to 1, so we set those two equal to each other and solve. Simple quadratic to solve, take the square root, and we're left with two x values that these curves intersect at, positive 1 and negative 1, which you can see right here. One other recommendation I'll kind of give, and it's not a requirement, but when you're sketching these graphs, you might want to only draw what matters. Of course, you could have kept this parabola going like this and drawn all of that in, but it's probably best to just focus on the area that really matters for these problems. So I didn't draw the whole parabola in. And of course, this line right here, where we have the arrow going around, is our axis of rotation. And that happens to be one of the functions that we're dealing with in this problem. And that's the line y equals 1. So in case you can't see it, that's the line y equals 1 right there. Okay, so we want to take this shape and rotate it around a horizontal line. The first thing I guess we can do is just kind of visualize what this might look like. Doesn't have to be done necessarily in your head perfectly, but getting a general idea of maybe what it looks like might help set these problems up. So when you take that shape that's above our line of rotation and flip it down below and kind of imagine it going in and out of the paper, we get this, not sure how to describe shape, but it's some sort of lemony kind of weird shape. Ultimately, the shape doesn't really matter in itself, we just need to understand how to set up the integral to find the volume of that shape. Since we're rotating about a horizontal line, and again it doesn't have to be the x-axis, we're going to draw our representative rectangle in vertically. And I'm going to label the height of that representative rectangle as big R with respect to x, R of x. Why with respect to x? Well, we're rotating horizontally. Why a capital R? Because that would be the radius of one of the discs that we're using to find this volume of the shape. Okay, so now that we have that set up, we have a good looking picture, we can go ahead and use our formula here. We need to find what big R is with respect to x. We need to find what that is, and then we can square it. So to do that, anytime you want to find these representative rectangles vertically, the height of them, that is, we need to take whatever the top of the rectangle is touching and subtract away whatever the bottom of the rectangle is touching. And I'm going to go ahead and do that on this side here, just so the main problem doesn't get too messy. So big R is going to be the function f minus the function g. The top of the rectangle is touching our f function. The bottom of the rectangle is touching our g function. Of course, we want to go ahead and write in what those functions were. So it's going to be the top function, 2 minus x squared, minus the bottom function, which was just 1. Of course, we can clean that up, and we'll just end up with 1 minus x squared. So, not too bad. Once we have that set up, which was just kind of like what we would have done in 7.1, what's different though in 7.2 is now we're using it in this formula to find volume. So don't, again, forget about that pi in front of the integral. We're going to integrate from negative 1 to 1, those are our bounds, of the function 1 minus x squared, all squared. And remember, 1 minus x squared was our function r. Once we do that, it's just a matter of our, again, integration skills. Again, if you really want to focus on the setup of these with the drawing of a nice graph and taking the time to set it up, I think that's definitely time well spent, because usually after this, you're going to end up with fairly simple integrals for the most part. Okay, so real quick, how do we integrate this function? We have 1 minus x squared all squared, so we can take that and FOIL it out. The reason we want to FOIL that out, especially since it's only to a second power, is we end up with these three terms, which are nice and easy to integrate. When we apply the upper bound of 1, we'll get 8 over 15. When we apply the lower bound of negative 1, we'll end up with negative 8 over 15. And of course, if we add those two together, we'll get 16 over 15. Don't forget about that pi in the front, though. When we multiply by that pi, we'll get 16 pi over 15 as the volume of that solid you saw at the beginning of this problem. Okay, don't want to neglect looking at a vertical rotation, so that's going to be this example. We want to take the graph of x cubed, which you can see here, the graph of y equals 8, which you can also see graphed, and the graph of x equals 0. Don't neglect that down here. So three graphs are making the area that we're going to rotate about the y-axis. And all of that here is in the picture for you. We have the three graphs, x equals 0, y equals 8, and the graph of x cubed, and we're rotating that about the y-axis. So again, you don't have to always visualize these perfectly, but I think some of these can be kind of easy to visualize. If you imagine taking this area here and flipping it about the y-axis, of course we'd basically end up with that same shape on the other side. I don't really think it's a good idea to ever really draw that in. I think you should just kind of visualize that in your head. So we'll end up with something like this. But the main thing I want to illustrate about this 3D visualization of what's going on here is that the disks in this kind of a scenario would need to be placed in horizontally. It wouldn't make sense to put them in vertically. So just be careful with that. If you refer back to that beginning slide we looked at, the second slide, when you rotate about a vertical line, we need to draw in our representative rectangles horizontally, which would mean the disks will be horizontal, which is what we need to find the volume of this shape. Okay, so let's go ahead and do that. We're going to draw in our representative rectangle horizontally because we're rotating about a vertical line. The only thing different here is it's still the radius of a disk, but it's going to be in terms of y. Okay, so what happens when we do this? Well, the only thing that changes with our formula is, again, everything's going to be in terms of y. So I think that's the first thing we need to realize. The second thing we need to realize is how do we find the length of these representative rectangles when they're horizontal? Well, again, think back to 7.1. When it was a vertical rectangle, it was the top minus the bottom. When it's a horizontal rectangle, it's whatever the right side of the rectangle is touching minus whatever the left side of the rectangle is touching. The right side of the rectangle is touching our function x cubed, but again, we need to write that in terms of y. So of course, we would just take this equation right here and raise all of it to a 1/3 power. Of course, when you raise x cubed to the 1/3 power, it's just x to the first, and of course y to the 1/3 power would just be y to the 1/3. Okay, so we're ready to go. The right side of this rectangle again is touching our function x cubed, or we got to do this in terms of y, so it's y to the 1/3 power. The left side of this rectangle is touching our y-axis, which would of course just be 0. And our bounds here, be careful, everything's got to be in terms of y, so we're integrating not from 0 to some x value, we're integrating 0 to a y value of 8. Okay, after that, like I said, with a lot of these problems, the setup is the, if not hard part, the most important part. And then after that, you usually will end up with a fairly easy integral. Not always, but a lot of the times. So of course, that minus 0 doesn't really count for much. So y to the 1/3 squared would be y to the 2/3. And now we just have a basic integral. Don't look at it as some u substitution or complicated integral, especially after what we've gone through before in this class. This one's just a straightforward integral, so we'll add 1 to the power, which is 5/3, divide by that new power, which is 5/3. Of course, I hope you got into the habit of not leaving that fraction in the bottom of that overall fraction. So of course, we'll multiply by the reciprocal, which would be 3 over 5 times pi. And then we still have y to the 5/3. After that, we can plug in the top bound of 8, we can plug in the bottom bound of 0. Careful here, this is a non-calculator problem, so be careful when you do 8 to the 5/3, remember this is really the 32 was really the cubic root of 8 all to the 5th power. And of course the cubic root of 8 is 2. 2 to the 5th power is 32. So you got to be good with some of that arithmetic without a calculator. But once you do that and multiply, you're going to get 96 pi over 5 as the volume of that shape. Again, you saw earlier in this example. Okay, the second part of this lesson involves still finding volumes of these things called solids of revolution. But what if we have a certain area that we're rotating about a line and it produces not a solid shape in a sense, but it's a solid 3D shape but with some sort of hole in it? Well, we're going to need to apply kind of the same technique using this disk method, but kind of extending that one step further, so to speak, and using what is called a washer. The disk method can be expanded to cover solids of revolution with holes in them. We're going to replace a disk with what is called a washer. So if you're not sure what a washer is, maybe you'll kind of be able to see it here in this next picture. So just imagine from that very first slide, that rectangle in the very first slide was connected, so to speak, to the axis of revolution. But now it's not. Now it's kind of floating above the axis of revolution, and we're still going to rotate about that line. When we do that, we're going to still get this disk shape, but of course, because it's floating above the axis of revolution, there's going to be a gap where there's nothing there. And this thing is, even though I'm labeling it as a disk here, this thing is what is called a washer. It's still a disk, but I guess it's a special kind of disk because it has that hole in it, which again is called a washer. And if you remember from before, I kind of kept saying, make sure you write the formula with the disk method with a capital R. The reason I said that is because now we have another R we have to deal with. We have this outer radius, if you want to call it that, which I'm calling big R, and then we have this inner radius, which we're going to call little r. Ultimately, we're still trying to find the volume of these disks, or washers now. So nothing's changed from all the problems we've looked at before. The only thing that fundamentally has changed, of course, is the volume of these washers. Since there's a hole in our disks, it's not going to quite be the same formula. The only thing that changes here is now we're going to take big R squared and subtract away little r squared. So it's really still the same formula. It's pi r squared w, but we need to account for that hole that's there given by the little r. So we need to take big R squared and just subtract away little r squared. Ultimately, that's really the only difference between these problems. So to kind of define this a little bit better, imagine we take this little shape here in blue and we rotate it about this line of revolution. I'm not sure if you can quite tell, but of course if you flip this over this line, we'll end up with that same shape somewhere down here. And then there's this giant gap right here that wouldn't be filled in. That's how we know that a washer is going to be the appropriate path to take. So if you kind of notice here, it wasn't maybe printed well on your paper. Hopefully it does come out good, but I hope you can see it here a little better. This top part that I'm highlighting is the part that we rotated about the line of revolution. This bottom one down here, which is what I drew in, is another solid piece. So these two pieces that I'm coloring in here are solid, so to speak. All of this, I guess I'll do a different color. All of this right here that I'm putting in green is just empty space. I suppose it's forming some sort of bowl shape, and all of that is just empty space, kind of like our disk that has a hole in it. And that's why we need to use we need to use washers instead of disks here. Okay, so these can be a little harder to visualize, but again, don't really get hung up on the visualization totally of what these are going to look like. As long as you can recognize there's going to be some sort of hole or gap in these 3D shapes, then you'll of course be able to see that you're going to use a washer instead. So I usually call the big R the outer radius, I'll call the little r the inner radius, and again, all that changes here is we're taking big R squared minus little r squared. And please take note, one of the gigantic mistakes that usually happens when you're first starting these problems, if you're not quite sure about this formula, is we're not taking big R of x and subtracting little r of x and then squaring it. Be careful, that's a very common mistake that I see a lot with people first trying to set these up. It's big R squared minus little r squared. Don't subtract the two r's and then square it. It's both of them squared separately, and then we subtract those two. Okay, so now let's take a look at a problem involving a washer. But maybe in a sense, let's pretend we didn't know it involved a washer, because you're not going to always know whether it's a disk or a washer. So we have these two functions here, and it's a bounded problem. They don't tell us from where to where we're trying to find this area. So we need to find where they intersect. Of course, just like you've seen before, we're going to set the two functions equal to each other. Here in this case, I didn't write it in, but we're going to take all of this and square it. When we square the left side, we're left with x. When we square the right side, we're left with x to the fourth. We need to move over the x by subtracting so we can factor this. Both of the terms have an x, and now we can set both of these factors equal to 0. Of course, the first one's easy, it's just x equals 0, and when we set x cubed minus 1 equals 0, we'll add 1 to the other side, take the cubic root of both sides, and we're left with just the number 1. So if we take a look at this graph, and again, be careful, I usually don't like drawing the entire graph, I just like drawing the piece of the graph that matters. We only care about these two functions where they intersect from 0 to 1. So again, be careful if you're not quite sure about this. This top function here, if you kept on drawing it, would be our square root of x function. This function right here that would keep on going up would of course be our x squared function. So hopefully you can see that. But again, it's kind of up to you if you want to draw the entire picture in, or just the piece of the picture that matters. Okay, so now that we have a good looking picture, I've labeled this little arrow here just to remind me that I'm rotating about the x-axis or a horizontal line. So what would this look like? Well, again, we don't really have to get a perfect picture of what this would look like, but ultimately we would need to realize when we rotate this shape below the x-axis and kind of rotate it in and out of our paper, we're going to end up with a shape that ultimately has a gap in it. All of this space right here would not be filled in with anything. The only solid part would be these blue parts. I never drew the blue on the bottom part, but would be the blue parts. If you need a kind of better picture than my little extra drawings in there, ultimately it looked a little something like this. All again of this area right here would be empty space, so that's why we know this is going to need a washer to make this problem work. Okay, once we go through all of that, and again, with a lot of these problems, I think the setup and the picture that you're going to draw is really the key to making them work out good. Once you kind of figure out all that, we can kind of start setting things up here. We're rotating about a horizontal line, so we need to draw in our representative rectangle vertically. Once we do that, the key to doing these, I think, is really labeling where the big R is and where the little r is. So be very careful. I guess listen carefully to how I describe this. Big R always goes from the outermost point on your rectangle to the line of rotation. Little r always goes to the innermost point on your rectangle to the axis of rotation. So be very careful. When you label these pictures, if you label it even slightly wrong, you're going to kind of mess up the setup for either big R or little r, or maybe both of them. So I'll say it kind of one more time here. Big R, which is the outer radius, always goes from the axis of rotation to the point furthest away on your representative rectangle, or I guess if you want to keep it simple, just to the top of the representative rectangle. The inner radius, little r, always goes from your axis of rotation to the closest point on your representative rectangle, or again, to keep it simple, just the bottom of the representative rectangle. Okay, once we have that set up, It's really just a matter of finding the length of big R and finding the length of little r. And again, keep in mind what we learned in 7.1. When you want to find these lengths, vertically at least, we always take the top minus the bottom. So for big R, the top of big R, this bracket I drew in, is touching the function the square root of x. The bottom of big R, which is represented by this bracket, is touching our axis of revolution, which is again 0. So big R, not too bad. Same thing for little r. This bracket that I'm using to show the length of little r, the top of it is touching the bottom of our representative rectangle, which corresponds to the function x squared. The bottom of this bracket for little r is touching the, again, axis of rotation, which is again 0. Like I've said in all of these examples, I think what we just did right here is the key. Of course, we're integrating from 0 to 1, and don't forget about the pi in front of the integral. That's the key to doing these problems. The setup is everything, because after that, it's a fairly simple problem. When we square this square root, and again, these minus zeros don't really count for anything. When we square the square root of x, it's just an x. When we square x squared, it's just x to the fourth. And then, of course, there's a minus in between those because we're subtracting big R from little r. After that, it's a very simple integral. When we apply the top bound of 1, we'll get 1/2 minus 1/5. And luckily, when we apply the bottom bound of 0, we just get a 0. 1/2 minus 1/5 is 3/10, and when we multiply that by pi, again, don't forget about the pi, it'll be 3 pi over 10, which is the volume of that 3D shape that has a hole in it that you saw earlier in this example. Okay, in this example, we're going to take a look at two very specific AP free response questions, no calculator. Take a moment to kind of read the details here, but the main thing I want to point out, because this happens quite a bit on the AP test, is they want you to write, but do not evaluate an integral. Realistically, with these problems, the setup, like you've been hearing me say, is the key. After you set it up, it's kind of already showing that you understand this concept of finding volume with either a disk or a washer. So usually in these AP problems, they won't even have you find that volume because they're going to test your integration skills in other types of problems. So just kind of keep that in mind. The setup here is the key, especially in these two examples here, because that's all you have to do is set it up. Okay, here we're given this area given by big R, and it's bounded by 2 squared of x, the horizontal line y equals 6, and the y-axis. So we have this area here. We want to rotate this area about the horizontal line y equals 7. So I guess I'll label it over here as y equals 7, just so you can see that that's the line that I drew in right there. Okay, so we're rotating about a horizontal line, so we need to draw in our representative rectangle vertically. So it comes down to recognizing whether this is going to be a disk or a washer. And if you visualize taking this area R and flipping it about this line that I drew, there's definitely going to be some sort of gap because we have this gap right here. When you take that area and flip it over that line, we're going to have this gap in between our two solid shapes or solid pieces. Because of that, it's of course going to be a disk. It's going to be a washer, which is of course just a disk method in a sense. Okay, so that means we need a big R and a little r. Big R always goes from, little r always goes from the axis of rotation to the point closest away on the representative rectangle. Big R always goes from the axis of rotation to the point furthest away on our representative rectangle. Kind of let that sink in, because again, that's the key to doing these problems, is if you can label your picture very clearly and appropriately, the setup of these integrals should be very straightforward. So again, little r goes from the axis of rotation to the point closest away on our representative rectangle. Big R goes from the axis of rotation to a point furthest away on our representative rectangle, which is again representing that washer that we're using to add up an infinite amount of to find the volume. Okay, so let's set up this integral. the volume is equal to, of course, don't forget the pi, the very common thing to forget. We're integrating with respect to x here, so we need to use x values. So it's going to be not 0 to 6, this is 9 right here, this is 6 right here. We're integrating with respect to x, so it'd be 0 to 9. And we need to do big R squared minus little r squared. So how do we find big R? Well, it's a vertical rectangle, so we need to take the top minus the bottom. That bracket is the thing you're trying to find the length of. The top of that bracket is touching the function y equals 7, our axis of rotation. The bottom of our bracket for big R is touching the function 2 minus the square root of x. We're going to take that entire thing, top minus bottom, and square it, and that's big R squared. So let's find little r squared now. Again, it's still a top minus the bottom. The top of this bracket, which represents the length of little r, is touching 7. The bottom of this little bracket that represents the length of little r is touching the function 6, and then we need to square that. I guess technically that's all there is to it, so to speak, but we're forgetting one little notational thing in that we need to show that we're integrating with respect to x, so don't forget to put the dx. Okay, here's one more example, basically the same kind of concept, but just so you can see another one of these set up. Here we're trying to rotate our region R here around the horizontal line y equals 1. Again, if you imagine taking this shape and flipping it up above that line, we are most certainly going to have an area that's not filled in, so to speak. There's going to be a hole. And because of that, we're going to need to use a washer. So we need to put our representative rectangle in vertically. And again, labeling the big R and the little r, I think, is going to be key to making these problems as easy as they should be. Big R again goes from the, little r goes from the axis of rotation to the point closest away on our representative rectangle. Big R goes from the axis of rotation to the point furthest away on the representative rectangle. And again, the reason for that is it's this inner radius, outer radius idea. Okay, we're ready to go now. Our volume is, of course, going to be pi times the integral from 0 to a half. Again, be very careful, we're doing this with respect to x. So that's a half right there, and that's, of course, 1 on the y-axis, so we're using x's. So it's going to be 0 to a half. And then we need to do big R squared. Big R squared is going to be a top minus the bottom. The top of big R, the bracket that represents the length of big R, the top of that is touching 1. The bottom of that is touching the function 8x cubed. And then we need to take all of that and square it. For little r squared, same idea. Top minus bottom. The top of little r, the bracket for little r, is touching the function 1. The bottom is touching the other function, sine pi x. We're going to take all of that and square it, and that's little r squared. Just like the first problem, technically I guess that's it, but for notational purposes, we have to put in that we're integrating with respect to x, so don't forget to put the dx. Okay, in these last two slides, all we're going to focus on is this idea of when do we use a disk and when do we use a washer. And to accomplish this goal of hopefully getting you to see this, I'm going to just use these functions right here to do a bunch of different problems. The area we're going to look at is given by these three functions, and all we're going to do in all these problems is set up the integral, and we're going to rotate this area, which is given by these functions, in several different manners. So let's take a look at what's going on with these functions. We're looking at the function square root of x, which you can see here in blue. We're looking at the function y equals 0, which would of course just be our x-axis, and we're looking at the function x equals 4, which you can see in red. So it's all of this right here, which is the area. Okay, so in this first problem, we want to rotate about the x-axis. If we rotate about the x-axis, and you can kind of visualize that, again, I wouldn't really draw these things in here. I think it'll kind of serve to just make it a little more confusing. But if you rotate it about the x-axis, we're not going to have any gaps in that three-dimensional shape. And since we don't have any gaps in that three-dimensional shape, this is definitely going to be a disk method. Since we're rotating about a horizontal line, we need to draw in our representative rectangle vertically. And luckily there's no little r we have to worry about. It's just the big R, which corresponds to the height of that representative rectangle. So we just need to take big R, and square it. To find the length of big R, we're going to do top minus bottom. The top of big R, which is again given by our representative rectangle, or the bracket that I draw in there, the top of that is touching the function square root of x. The bottom is touching the function 0, which is just our x-axis. And that's it. We're integrating with respect to x, so our bounds need to be the x bounds, which would be 0 to 4. And that's it. We're not going to simplify this at all. We're just going to leave it like that, just to show that we understand the setup of these volume problems. In this problem, again, it's the same area we're taking, but now we're rotating it about the vertical line x equals 4. If we rotate it about this vertical line x equals 4, we need to draw in the representative rectangle horizontally. And again, if you can kind of visualize this here, if you take that shape and rotate it about the line x equals 4, we'll end up with just that shape on the other side, kind of going in and out of your paper, so to speak. But ultimately, the thing you need to realize is there is no gap. There are no holes in that three-dimensional shape. Because of that, this is going to be another disk method. And just be careful here. We're not going to use our function square root of x. You might want to take note over here at the top. Anytime we're going to use everything in terms of y, x would be equal to y squared. So kind of keep that in mind, any of these ones that we need everything in terms of y. Okay, so our representative rectangle corresponds to the radius of our disk that we're using here. So we're just going to label that as r with respect to the function, or with respect to the variable y. Okay, so to find big R, which is going to need to be squared, we're going to have to do right minus left. The right side of that bracket, which is giving us the length of r, is touching the function 4. The left side of that function, of our bracket, is touching the function square root of x. But again, be careful. We're doing everything in terms of y, so it's going to have to be y squared. And then on top of that, now our bounds are not 0 and 4. Our bounds need to be 0 to 2. That's the area we're looking at in terms of y. We're going from 0 to 2 because everything has to be in terms of y. And again, don't forget, we got to put that pi in front of the integral, a very common thing to forget about. Okay, one more here. We're going to take our area yet again and rotate it about the y-axis. And here's maybe where the visualization really will come in to help you. If you take your shape and rotate it about the y-axis, we'll end up with something approximately like that. But the main thing you need to realize is there is most certainly a gap. There is most certainly some sort of hole here in this three-dimensional shape, whatever it would look like. So of course, in this case, we would definitely need to use a washer. Again, we're rotating about a vertical line, so we're going to do everything in terms of y, which means we need a horizontal representative rectangle. Again, this is a washer, so be very careful. Little r goes from the axis of rotation to the point closest away on that representative rectangle. Big R goes from the axis of rotation to a point furthest away on that representative rectangle. Once you get those two kind of visually set up there, it's just a matter of doing right minus left for both of them. Big R squared. The right side of that bracket for big R is touching the function 4. The left side of the bracket for big R is touching the function 0, our y-axis. So for big R squared, it's going to be right minus left, 4 minus 0 squared, all squared. For little r, the bracket is touching our function square root of x. But again, we're doing this in terms of y, so that's going to be y squared. The left side of the function, the left side of this bracket for little r is touching 0, so it's going to be y squared minus 0, all squared. Don't forget the kind of little details here. Don't forget the dy, and don't forget the pi in front of the integral. Okay, two more examples here of taking the same shape and rotating it in different ways. Here we want to rotate about the line x equals 10. I really don't have space to animate this here or draw in the picture because the problem is we're taking the shape here again and flipping it about this vertical line, which would kind of go off screen here. But ultimately, especially in a problem like this, I think you can most certainly see there is a giant gap right here. And when you flip it on the other side, of course, that gap also exists. So this is most certainly going to be an application of a washer. Since we're rotating about a vertical line, we need to draw in our representative rectangle horizontally. So let's label big R and little r. Big R extends from the axis of rotation to a point furthest away on our representative rectangle. Little r extends from the axis of rotation to a point closest on the representative rectangle. Again, once you draw this picture, label it, everything's clear, I think these setups can be very, very simple. So let's go ahead and set this up. Again, we're doing everything in terms of y. Big R squared is going to be a right minus a left. Little r squared will also be a right minus a left. So when we set this up, big R squared, the right side of that length, is touching 10. The left side is touching our function square root of x, but be careful, everything's in terms of y, so y squared. And then all of that is going to be squared. Again, it's supposed to be big R squared. And now we can do the subtraction of little r squared. The bracket for little r, the right side of it is touching 10, the left side of it is touching 4, right minus left, 10 minus 4, and then we take all of that and square it. Again, don't forget about the tiny details here. We need to put the dy, we're integrating with respect to y. We need to put the pi in the front, and also don't make, again, I don't want to say it's too common of an error, but a common error. It's not 0 to 4, we're doing everything in terms of y, so it would be 0 to 2, which is the upper bound when you're looking at the y direction. Okay, one last one here. We're taking our shape yet again and rotating it about a horizontal line, y equals -2. Again, if you kind of imagine taking the shape and flipping it about the line, which I again wouldn't have space down here to draw, you can most certainly see there's a big gap right here, and when you flip it about that line in 3D space, there's definitely another gap right there. So we have a hole. And when we have a hole, we need to rely on a washer. We're rotating about a horizontal line, which means we can go back to using a vertical representative rectangle. Okay, so like you've heard me say many times, and I've been trying to be very deliberate with how I say it, so you can kind of see how to set up big R and little r. Big R extends from the axis of rotation to a point furthest away on the representative rectangle. Little r extends from the axis of rotation to a point closest away on that representative rectangle. Once you kind of draw those two lengths in, here in this case it's just a matter of doing top minus bottom because we're looking at this vertically. Big R squared would be a top minus a bottom. Little r squared would also be a top minus a bottom. So what's that going to look like set up? Again, I'm not going to simplify this at all. I kind of hopefully want to make this nice and clear in terms of the setup. We definitely need our pi in front of the integral. Be very careful, we're doing everything now with respect to x, so it's going to be 0 to 4 now. Big R, the top of that bracket is touching the function square root of x. The bottom of that bracket, which represents the length of big R, is touching the function -2. So it's top minus bottom, so square root of x minus -2, and then all of that needs to be squared because it's supposed to be big R squared. From that, we need to subtract little r squared. The top of the bracket that represents the length of little r is touching the function 0. The bottom of the bracket that represents the length of little r is touching the function -2. So top minus bottom will be 0 minus -2. I'm purposely not simplifying that, just so we can see that setup. And then all of that needs to be squared for little r squared. And then just don't forget to end all of that with the variable of integration, the dx, at the end.